Hello. I would like to explain something about how to manipulate your orbit in Rogue System. In order for us to understand what we're doing, we need to explain a few bits of the reticles, basically these symbols, what they mean. This symbol represents our forward direction. In the opposite direction, of course, we have a reticle which shows where we have come from. There is another reticle here, and opposite to this one, which basically are at 90 degrees angle to the forward and the forward and backward reticles. And then there is, these are called normal and anti-normal reticles, basically up and down reticles. Orbit manipulation in Rogue System at the moment with this fire arc is largely about reading off these values. These values, understanding what they mean and knowing how to change them, is paramount to controlling your craft. Now, you may be thinking that, what, isn't it just enough to just look outside the craft and just, you know, just check where you're going? But I'm like, you don't have to look for a very long time to be able to tell that. It's bloody hard to tell where you're going. And I'm like, you could be going in a perfectly straight line, but your velocity is not high enough, and you end up crashing on the other side of the moon. It could be those kind of cases. So, without further ado, what do these values mean, and what do they represent, these names? So the altitude is maybe the easiest one, is basically the distance to the surface of the moon. So that's not strange. Now, apoapsis and periapsis aren't as easy. Apoapsis is the point of our orbit, in our orbit, which is furthest away from the moon. And vice versa, the periapsis is the point in our orbit which is the closest to our moon. Currently, we are at an altitude which is increasing, and so we are approaching our apoapsis, and so the time to apoapsis is 1 hour and 15 minutes. Alright, well, I'm going to show you with a diagram, because diagrams are awesome. So, what you see here, this orange blob is meant to be a rocky planet or something like that, and the red dot, which is closest to the rock, it's the planet, is the periapsis. The other opposite dot is the apoapsis, the point furthest away. Now, let's see here. So, yes, that's basically that. And next is the true anomaly. It is an angle, as I understand it, but I cannot for my life figure out what to use it for. I've been able to go from one moon to another, or a planet to another, without any problems, without even bothering thinking about what the true anomaly might be. So I'm gonna skip it for now. I would be very happy to learn what it's used for, but for now I'm just gonna leave it out. Velocity is, of course, the velocity of our orbit around this moon, or any object which we're orbiting around. And the period is, of course, the amount of time it takes for us to complete one revolution of our orbit. Now, eccentricity is another kind of tricky value, but way too useful to be ignored. eccentricity, when it is 0, means that we are flying in a perfectly circular orbit, pretty much. If the eccentricity is between 0 and 1, as in it is not 1 and it is not 0, then it is basically an ellipse, like this one. Now, if the eccentricity is 1 or larger, it becomes a so-called hyperbolic orbit, if you could call it an orbit at all. Where basically what it means is that you just whiz past the gravitational attractor. And so, if you have this situation, you could very well have like a non-zero, a non-infinite periapsis. Remember, periapsis is the point of our orbit which is closest to the gravitational object, but we can have an infinite apoapsis, meaning that it's away in infinity, and you know, it's you can't basically find it in our universe. So that's basically how you interpret that then. Alright. Now the zenith angle isn't as complicated as eccentricity or even true anomaly, but it still kind of requires a diagram to be properly explained. And what it basically is the angle between the radial out vector from the planet, between that vector and the spacecraft's forward pointing vector. So what does that mean for us? Well, we currently have a zenith angle which is less than 90 degrees. Remember, the zenith is basically, if you're standing on a planet or a moon or whatever, the zenith is basically the point which is straight up, just straight above your head. So that angle to our forward reticle is less than 90 degrees, which means that we are basically currently heading slightly away from the moon. Alright. And before I go on, there are a few more things I have to explain. There are, you could call them kind of orbits, basically impact orbits. The one to the left is an example of an orbit. If you're, for example, whizzing through space and all of a sudden you're coming up against a planet or moon or any other large gravitational attractor, and in this case you would find that your apoapsis is at infinity. It would say that you're at an escaping trajectory, but your periapsis would basically say that you're on an impact course, that it would give you an impact warning. And it would be kind of similar with a diagram to the right, but there you would have, you see, because there is a point which is not infinite, which is basically how far we get into space before we come crashing down again. We will have a non-zero, non-infinite apoapsis, but our periapsis reading would say that we have an impact warning. Alright. So, without any further ado, let's alter our apoapsis a little bit. Our altitude is fairly close to our periapsis, and the way you change, it's advisable to only change your periapsis and apoapsis when you're at the opposite point. So we're kind of close to the periapsis, so we're in a position to change our apoapsis, we're pointing forwards, so I enable the boost deflection, meaning that we'll basically be accelerating backwards, or decelerating, so to speak. Right. So if we enable that booster, our apoapses will be decreasing steadily. Now notice how our periapses started to decrease as well. That's because our altitude was not particularly close to the periapses. We should have been even closer before we should have attempted this. And but now then we've changed our orbit, and this is basically the easiest way of doing this, of changing your orbit. But it becomes a little bit more involved when you travel from for example, from one moon to another. If you want to go to that moon over there, then you have to be a little bit more clever about how you manipulate these things. As long as when you're dealing with a flux drive, though, you don't really have to think very much about orbit mechanics at all. That just goes to show how it's not super OP. It's not overly powered, this flux generator, but with this constant G motor, we are capable of traveling at really considerable speeds from one celestial body to another in no time. I'll commence and do this orbital transfer, and I'll cut forward. I'll cut this video forward when I actually get there. Yes, so we travelled all the way from that moon over yon, and we're pretty close to the other moon. Well, I was pointing to this other moon, which is to our right somewhere, but well, whatever. I selected this one on the target screen, and I flew all the way over there. Now, we are still approaching. When you travel from one celestial body to another, this figure becomes important as well, just to check that you're actually approaching the body at all. And let's check our readings here now. The altitude is decreasing fast, just parallel to this one, of course. But our apoapses and periapses are more worrisome. The apoapses is saying escaping, which basically means that we came whizzing from over yon, and yeah, we're basically heading over there, of course. And the periapses says impact warning, which of course means that we're heading straight to our death. Now let's avoid that. And well, it's just like a blow in karate. When somebody makes a punch, strikes a punch straight at you, the easiest way of deflecting it is by deflecting it sideways, towards the side. So we shall do that to begin with. Our eccentricity will increase quite drastically. A good rule of thumb is that the higher the eccentricity is, the faster it tends to change when you apply a deflection to your orbit. Now, this is going to take a wee while, so I'm gonna speed things up a bit. There we go. And let's decrease our thrust like that. Notice now how our apoapsis says escaping, while our periapsis says 300 kilometers. We now have this situation where we will be whizzing past the moon unless we apply a braking force. Our eccentricity is rather high, and remember, an eccentricity which is higher than 1 means that we'll be whizzing past this thing, and like I said, the higher the eccentricity is, the faster it changes, vice versa. The lower it is, the slower it changes. So, only thing we can really do is to sleep until our computer recognizes that we have arrived and perform some time compression. You can actually see already now how it's approaching kind of fast. Remember, our velocity on the other moon was about 1,200 meters per second, and we're currently whizzing by. We will be whizzing by at 12,000 meters per second, almost 10 times the speed we had before. So we'll disable the throttle lock for the flux drive and decelerate slowly. Notice now how if I point the reticle straight at our direction vector, our periapsis will slowly but surely decrease. In order to avoid that, ideally you want your periapsis to increase slightly rather than decrease slightly. And you avoid that decrease in periapsis by pointing slightly towards the planet itself. Now we have to increase our deceleration rate slightly because we're gonna be whizzing past really quick if we're not doing something about this. And we're still on an escaping trajectory. Basically just trying to align this deceleration vector. That orange reticle shows us where shows us the opposite direction of our deceleration, and it's changing slowly because we're so close to this moon. I'll slow down the time compression and see if we're actually gonna overshoot. No. As soon as the eccentricity reaches the order of about 1, as in, I guess, between 1 and 10, then we're kind of fine. We're still on an escaping trajectory. Let's see, gonna lower the periapsis a little bit. And then the most important values we want to look at this point is the zenith angle, the eccentricity, the periapsis, and the apoapsis. Basically, when the zenith angle is 90 degrees, we're kind of traveling parallel to the surface of the moon. We're currently not. We're currently at a slight downwards angle. So when this zenith angle starts to approach 90 degrees, that's when you have to start to worry about whether or not you will be able to decelerate enough such that you will actually be able to establish an orbit around the orbital around the gravitational object at all. The velocity is still high. We're getting there, and very soon there we have an eccentricity lower than 1, and such that we have a non-infinite apoapsis, notice how quickly it goes down. And yeah, but the eccentricity, like I said, is changing real slowly the lower it gets. Remember, we want the eccentricity to reach about 1. What the? Perhaps this is getting a bit too low. It's just wise to give yourself some leeway so that you can actually do some mistakes and still have time to fix them. Right, we're still 8 minutes away from our periapsis. I'm gonna start decelerating now because the zenith angle is approaching 95 degrees. When we reach 90 degrees zenith angle, we want to make damn sure that that our apoapsis and periapsis are as close to each other as is humanly possible. Let's set the autopilot to keep track of the forward direction, the prograde direction. Let's see here. Notice how the zenith angle, the change in the zenith angle, slows down quite dramatically as our apoapsis and periapsis values start to approach one another, and yeah, it's pretty close to one another, I dare say. It's close enough, and that, ladies and gentlemen, is basically how you fly from one moon to another, and then establish a stable orbit around the moon. I'm pretty certain it would certainly save your hide if you can read these values and tell it whether or not you're gonna crash into the celestial body you're orbiting or not. That's for certain. Before that, you have to go to the stars and shit like that, you know. Whatever. Like I said, the most important values are the eccentricity, the zenith angle if you want to make a really nice circular orbit, and the apoapsis and periapsis, to know how to read them off. And that's pretty much it. Thank you for watching.